Hello everyone, welcome to part 3 of our ecology notes. So today we're going to explore thermal energy transfer in the atmosphere. And when it talks about thermal energy transfer, what we actually mean this is the movement of thermal energy from an area of high temperature to an area of low temperature. So when we're doing thermal, we're dealing with temperature. And energy in this way can be transferred 3 different ways. We can have radiation, we can have conduction, and as you can probably see underneath, we can do convection as well. And in these forms, energy is transferred from one location to another to reach balance, equilibrium, by moving the particles around. So it's through that kinetic energy that we reach balance. So for radiation, this is the transfer of energy via electromagnetic waves. For example, the rays from the sun to the earth, or you're a bonfire. So when you have a bonfire to your face, the heat that radiates out of the bonfire and it comes to your face is transferred through these electromagnetic waves through the air. Conduction, on the other hand, we're going to just use a different color just so that we don't get these guys confused. This is the transfer of energy via direct contact. So this can take place in solids like a hot stove. When you touch a hot pan or a hot stove. We have that conduction. Whereas convection, the last one is convection. This is the transfer of energy through the movement of particles from one location to another. Okay. And it can occur in fluids or in gases to form what is known as a current. Oops. You can have a current of air or a current of water. Convection currents in the ocean, for example, are created by warmer air rising up at the equator and then is going to be falling down wherever it cools. So created by warmer air rising up in the equators and traveling to the poles where it cools. Okay. I guess I should I'm going to shrink this down a little bit. Let's see if it'll allow me to shrink it. 1, 2. I'm going to rewrite it then, if it won't let me shrink it. because I also want to say, I wrote it too big. Created by warmer air rising up at the equator and then traveling to the poles where it cools and sinks. And then again, starting a cycle, right? So then once it's low, it goes to the equator where it gets warmer and it rises up. It is like boiling water. So let's say that I have air at the equators, the air gets hot, so hot air rises, and then it travels to an area where it cools off, and as it cools off, it sinks, and then it sort of does the same thing. And so when you have a pot of water, it's the same thing. This is where our heat is, and our water is down here, and then the water is going to go to the top, pushing cold water down. Cold water is going to get heat up by the flame, and it's going to go up. And so it creates sort of this circulation pattern, okay, that we see there, that we would see this in our planet as well. So you can see it right here. The same process that occurs in the ocean water occur in the gases of the atmosphere. So we see the temperature, let's use black. The temperature of the atmosphere tends to increase as we move to the equator. And then as the gas particles are heated up, they move further apart. So less dense, they become less dense or lighter, and therefore they rise. In areas close to the pole, the opposite happens. The temperature of the gas is cool. The gas particles contract and move closer together, and that makes them more dense or heavier, and therefore they tend to fall. And so when we get to the wind on our planet, what wind is just a global scale convection current. Really what it is the movement of air from areas of high pressure to areas of low pressure. And so you can kind of see here the air is at the equator, it heats up, so it goes, and then as it gets into these northern latitudes, it gets cold and therefore falls back down. And the same goes here. I have the air that is coming here, it's heating up, and therefore it's going to go higher up. And then as it reaches these latitudes, it's going to fall down. And the same thing happens here. We're starting here where it's hot, and it's going to increase in temperature and go up, and then as it cools off, and then at the poles is the same thing, because here it's going to be the coldest, so you're going to see that it sort of rises up and then it falls down. And you're going to see why we get sort of these patterns in just a second. The Coriolis effect is what you're seeing here, and the Coriolis effect is the deflection that occurs to any object from a straight path, from a straight line, by the rotation of the Earth. So the Earth rotates around its axis, it spins on its axis, and so what you're going to have is you're going to have a deflection of the winds, and the winds are going to rotate right in the northern hemisphere, and they're going to rotate left in the southern hemisphere. Without the spin of the Earth, you would have the winds in a straight line. And so the winds are going to be rotating this way and this way. And so you can see that when I have this spin in this direction, it's not going to be straight up and down. It's going to be affected by the Coriolis effect, and therefore it's going to be, the wind is going to be blowing in this direction. And then when I go into another latitude, what you're going to see here is I have again warming up and then cooling off, but because of the rotation, I'm going to have the winds are going to blow in the opposite direction. Okay, and so you're going to have, and that's why they're called easterlies and westerlies. Whether they, you can see here, easterlies, right? And you're going to have, these are going to be the westerlies, and then the doldrums are the ones that flow straight. They don't actually have any sort of direction. Okay, so global wind patterns. Let's look at the global wind patterns. So what's going to happen is that these currents, the wind causes the transfer of thermal energy from warmer areas to cooler areas. And so this maintains sort of a thermal equilibrium on the planet. If you remember last time we said something about energy deficit versus energy surplus, right? Now when it comes to the jet stream, these are fast moving winds. So this is fast moving air in the stratosphere. And the reason why it's so fast is because it's not subject to friction. Whereas the surface winds that we have on the surface of our planet, because of the geography of the planet, whether you have hills, trees, apartment buildings, whatever it might be, there's friction, and therefore it slows down the wind. Okay, and they got their name from pilots who discovered them, because when you were flying in one direction from the US to Britain, then you would go faster than if you traveled the other way from Britain to USA, right? So how come in one direction the flight, let's say, is 10 hours, and then on the other direction the flight is 12 hours? Okay, so that's how they figured it out. It's because you're either flying with the jet stream and therefore it's quicker, or against the jet stream and therefore it's slower. Okay, phase changes in global energy transfer. Now we know that water is going to be absorbing energy. So it absorbs energy in the form of heat, for example, when evaporating. If I want water to turn from a liquid to a gas, I'm going to need to absorb heat, and releases it during condensation. Oh, I don't know why I put brackets here. When evaporating, and releases it during condensation, causing air to warm and rise and form clouds, which can then, lead to thunderstorms, which we've seen lately. And then more severely, hurricanes, tornadoes, right? All of these phenomena are due to the uneven sort of heating of air. So the hydrologic cycle, the cycle of condensation, evaporation of water, plays a major role in climate. Okay, so when we say that water has the capacity to hold heat, we can also say that water has a high specific heat capacity. So what does that mean? It means that it takes a lot of energy to change the temperature of water. If I take something like aluminum foil, it's used in baking a lot because it has a low specific heat capacity. It doesn't take a lot of heat, a lot of energy for it to heat up. And at the same time, it doesn't take a lot for it to cool off. So once we take it out of the oven, you can easily grab aluminum foil from a corner and pull it off from your, what's it called? From your pan. So this property then affects the temperature of different areas on the earth. So for example, compare a coastal city to an inland city. A coastal city, the weather is quite more mitigated than it is in inland cities. So you have a more temperate conditions, whereas in inland you have more extreme conditions, more temperature fluctuations. And the reason for that is in coastal cities where you have water, the water will absorb heat during the day and then release it slowly at night. And so the temperature tends to remain in the same kind of a temperature range. Whereas in inland cities where you don't have the water, as soon as the sun drops from the horizon, it tends to get quite cool compared to during the day. Okay? And we were look at this property just now by sort of explaining the origins of chemical potential energy. So where does sort of this whole energy start from? Okay, so we know that the source of any energy is always the sun. And then the sun is going to be transferred to plants. They're going to perform photosynthesis, and then the plants are going to be being eaten by animals. And then those animals will die, and they will decompose, and they will form fossil fuels, whether it is gas or coal or natural gas or oil. And then that oil can be used to run things like cars, producing carbon dioxide that goes up in the atmosphere. That carbon dioxide is taken up by the plants, returned into the cycle, and sort of kind of repeats itself. So during photosynthesis, the energy that originates from blank is converted to blank energy and stored in chemical bonds. So we know that it's going to be energy from the sun, and that energy from the sun is going to be then converted to chemical energy. So these are kinds of questions that you can think of in terms of where energy starts from. And then from the formation of methane to its eventual use in automobile fuel, the order of the processes listed above is, so from formation of methane. So we're going to need the formation of methane. We need it to start at the sun. And then eventually we're going to have that sun being picked up by plants. And then it's going to be bacterial decay where either the plants or the animals die. And then we're going to get to that combustion eventually. Okay. So how does water play a role in all this? 70% of the earth is covered by water, and therefore it's going to play a major role in that distribution of the thermal energy. And some of the properties of water that make it so special is the fact that it has that high specific heat capacity, and also that it has a high heat of fusion and heat of vaporization. So the amount of energy that it takes for it to melt or freeze, and the kind of energy that it takes for it to become a gas, to evaporate or condense. So that's what the heat of vaporization. So it takes a lot of energy for it to melt or freeze or to evaporate and condense. And because it's transferred through the hydrologic cycle, obviously, anytime that we have one of those energy conversions, we are carrying that energy with us. So how does water do the things that it does? Well, we know that water is a polar molecule, right? So when I look at H2O, it has a positive end and it has a negative end. And then the positive end of one molecule is going to be attracted to the negative end of the other. And then the negative end of one molecule is going to be attracted to the positive end of another. So the water is adhesive, which means that it sticks to other polar molecules. So other molecules that, just like water has a positive and a negative, the water is going to be attracted to them. And it is also cohesive because it sticks to itself. Again, water molecules are going to be attracted to other water molecules. Okay, so we can see here, if I were to draw sort of a hydrogen bond, a hydrogen bond is a bond that forms between a hydrogen and either nitrogen, oxygen, or fluorine. And it's not an actual bond like these. Like these guys right here, these are known as covalent bonds. Right? So if I were to draw an oxygen and two hydrogens, okay, this is known as a covalent bond. This is a bond within the molecule of water. Whereas a hydrogen bond is one that sort of is a loose attraction that happens between one water molecule and another, because this guy is attracted to that guy. So this is a hydrogen bond. It's more of an attraction. It's called a bond, but it's not. They're not attached together. They're attracted to one another. So these is two separate water molecules attracted to one another. Okay. So temperature, when we're looking at temperature, what we have is not heat. Okay, temperature is the measurement of how much the molecules are moving. So really, it is the measurement of the thermal energy or the kinetic energy of a substance, whereas heat is the transfer of that energy between two bodies that are at different temperatures. So heat is when I have something on one temperature, one of the other, and the energy is transferred between the two of them. Okay. So now we have water in all three phases right here, and by either adding or removing energy, I get these phase changes. So here we have some heat. We have a transfer of energy, either in one direction or in the other. Okay, if I add energy, I melt ice, I evaporate water into a gas. If I remove energy, then water vapor will turn into liquid and liquid will turn into gas. That makes sense. Okay, so how do I calculate the energy that is required to either raise the temperature of water or to change the phase of water? Well, I use a couple of different formulas. So the first formula we're going to see here is Q is equal to MC delta T, where Q is the amount of energy needed. In joules, M is the mass in grams. Delta T is the change in temperature that I want to experience, and it's in degrees Celsius. And then the last thing is this C value. C is going to be a constant, and for water, it is the specific heat capacity, which is 4.19 joules per gram per degree Celsius. So what does that unit mean? It means that for every gram of water that I want to increase by 1 degree Celsius, I have to add 4.19 joules of energy. Okay, so for every gram of water and for every degree Celsius that I want my temperature to go up or down, I have to either add or remove 4.19 joules of energy. Okay, so in order to calculate this, we're going to use these questions. And for a question like this, just remember that one other thing that I'm not sure if you are aware is that 1 milliliter of water is equal to 1 gram. okay? So if I have 100 mils, it's the same thing as me saying I have 100 grams of water. And I'm raising the temperature from 5 to 20, so how much energy is added? So Q is equal to MC delta T. So I have 100 grams, 4.19 joules per gram degree Celsius, and I want to increase the temperature by 15 degrees Celsius. And so you can see here then, grams and grams cancel, degrees Celsius and degrees Celsius cancel, and so my answer is 6,300 or 6,290. So I'm going to need 6.3 kilojoules since I need my answer to be in 2 significant digits. Okay, so go ahead and try the other questions on here. In number 2, you're solving for delta T. You should get 2.4 degrees Celsius. And in the next one, you're again calculating energy. So you can get 0.15 kilojoules or 1.5 times 10 to the 2 joules, okay? And you're dealing with aluminum. So they are giving you the C for aluminum, okay? It's not the C for water, so it's not 4.19. It's going to be the C for aluminum, okay? So you're going to be using that one. And we can see here, we talked about water being a heat sink and then a heat source. So a sink during the day, it absorbs the heat, and then a source at night, it can release that heat if we need to. There's a couple more questions here that you can try with Q equals MC delta T. I'm going to leave those for homework. And we're going to get into calculating energy when we have a phase change. So here you can kind of see the phase changes and transformations. They are physical changes, therefore there is no temperature change, okay? So no temperature change during a phase change. So what that means is that water freezes and melts at the same temperature. Water will freeze at 0 degrees Celsius. Ice will melt at 0 degrees Celsius. That's where we have the phase change. Okay, and then we can see here that the transformation can be both endothermic. We put energy in. Remember that endo means in. And exothermic transformation means energy out. So remember exit. And so when do I have to put energy in? When I want to melt or when I want to boil. So by adding energy, what I'm doing is my energy is going to be in the positive. Whereas when I'm removing energy, for example, when I want to freeze, I have to take heat away from the water. I have to put it in the freezer. I have to take heat away from the water, and therefore that's going to be a negative. And what we see here is we have the formula where we have delta H fuse, which is the heat of fusion. So that's what it stands for. So this is the heat of fusion. And this is the heat of vaporization, which are, again, they're going to be two givens. Okay, so they're going to be two variables that are given to you. And it's equal to Q, which again is the amount of energy in joules, and N this time, which is the number of moles. So we're not going to be dealing with mass, we're going to be dealing with moles. And to remind you again, just in case from Science 10, we have a formula to figure out the number of moles. Okay, so I'm just gonna remember that number of moles is mass over molar mass. So we'll get to that when we do some of these questions. All right, so what are the two given? The two given are the heat of fusion for water is 40.66 kilojoules, and the heat of fusion is 6.01. So you can say it takes a lot more to make water evaporate than it does to make it freeze or melt. Okay, so let's try a couple of questions. How much energy is released to the environment when 20 moles of water condenses? Okay, so if I have Q is equal, and I have delta, so first of all, condensation, so I'm dealing with vapor, so I gotta have HVAP is Q, and you can see here divided by N. Then if I have to figure out my Q, it's just my N times my HVAP. And so I have 20 moles. And my HVAP is 40.66 kilojoules. And so what I get is 813 kilojoules. Okay. And it is condensing. So I want to condense. So when I look at this, condensation should be a negative number. So here, this is a negative 40.66. And so this is a negative number. We are removing heat, okay? Released into the environment. So calculate the energy change, 5 moles of freezing water. You can do that one, same kind of idea. Okay, we are freezing water. So we are freezing water, we are solidifying. So again, if we are solidifying, we're gonna have a negative number, negative H fuse, right? Remember, it gives you the option of either positive or negative. So you can do that one. And then it says calculate the energy of 400 grams of water that is evaporating. So again, I'm gonna have to evaporate the water. In this case, it's the opposite of condensing. So I'm gonna have, first of all, the number of moles. I have 400 grams of water. The molar mass of water is 18.02 grams per mole. How do I know that? H2O. H is 1.01 grams per mole. And then oxygen is 16.00 grams per mole. But don't forget that I have 2 of these guys. And so 16 plus 2.02, I get 18.02. So I get 22.197 ... Keep it all in your calculator, moles. And then I have to figure out the Q. And so I have this many number of moles times negative HVAP. And so I'm going to get 903 kilojoules negative. So it's going to be energy that is. And then it says the energy evaporating water. I have to put energy in. So it's going to be an endothermic. I'm going to be adding. The water is going to be absorbing the energy. Okay. So then try the last one as homework as well. And then we get it to a heating curve. A heating curve just shows the different transition that water is making as it's heating. So I can have from really, really cold ice and then bring the temperature up to 0. And then here I have my melting. And then here I have the temperature increasing all the way up to 100 degrees. Here I have evaporation. And then here I have my heat, my gas that can also increase in temperature. Okay, so here in this section right here, this is I have ice increases in temperature. And so because of that, I have Q is equal to MC delta T. Anytime that I have a slope, I'm changing in temperature. Here, I have water increasing in temperature. And so again, I would have a Q equal MC delta T to figure that out. And then right here, I have steam increasing in temperature. And again, it would be a Q is equal to MC delta T. In these guys right here, I just have water turns to steam. That's just a phase change. And so here I would have my Q is my N times my delta H vap. And here I have my ice turns to water. And so again, I would have Q is equal to NH fuse this time because, and so that's how those formulas are going to work. All right. And then one more question I want you to look at. In order to calculate the amount of energy required to heat the unknown compound from X to Y, so you need it from here to here, so from there to there, this whole section. The characteristic properties listed above that must be known in addition to the information given in the graph are which properties? So I have the temperature already. So what else am I going to need? Well, here I have to change. It's an unknown compound. I have two phase changes. So here I go from a solid to a liquid. So it's going to be the heat of fusion. So I need to know that. And then here, this is going to be just increasing in temperature. And so I'm also going to need a specific heat of that particular substance. So the answer here is 3 and 4. Okay. So continue, practice with these questions. These are your homework. I can give you the answers next time. I can post it already finished and completed for you guys to have a look. And the next time we do this, we are going to be on biomes. Okay, so tomorrow at the meet, you can ask any questions or we can even go over these ones as part of our Google Meet. Okay, we will see you guys then.